Okay, number 16, we need to solve. We have another exponential equation here. 4 times 5 to the 2x equals 24. So this is the exponential part of our equation. Before we can solve, we need to isolate that. You cannot distribute this 4 into here because of the exponent. So instead, what we want to do is divide both sides by 4 to isolate the exponential part of our equation. So we have 5 to the 2x equals 6. Then we can use the definition of logarithm or take the log of both sides. I think I'm just going to take the log of both sides. So if we take the log of both sides of our equation, the log of 5 to the 2x equals the log of 6. We do that because then we can use one of our properties of exponents that properties of logarithms that lets us take this exponent and move it out front. So then on the left-hand side, we have 2x times the log of 5 equals the log of 6. Again, keep in mind, we're trying to solve for x. Right now, it's 2 times x times log 5. So to solve for the x, we need to divide by 2 times log 5. We'll do it on both sides of our equation. And 2's cancel, log 5 cancels. We get x equals log 6 over 2 log 5. There are equivalent answers that could be correct. This is what we call our exact answer. Okay, our exact answer is the mathematically symbolic answer because logarithms aren't exact. If we put them in our calculator, they are going to be rounded because they are non-repeating values typically. So that is our exact answer. This one also asks for the answer rounded to 2 decimal places. So we have log of 6 on the top and 2 log of 5 on the bottom. We round that to 2 decimal places, we get 0.56. X is approximately equal to 0.56. That is our approximate answer. Next up, number 17, another exponential equation to solve. A little bit different technique here. So if we could, we would rewrite these to have matching bases because from there it's a pretty easy solve where we set the 2 exponents equal to each other. But 3 and 5 cannot be rewritten in any way that they have a matching base. So our technique here instead has to be to use our logs and take the log of both sides of the equation. Once we do that, the reason we do that is because then we can take that exponent and pull it out front by one of the properties of logarithms. So what we end up is 2x log 3 equals x plus 1 log 5. Keep in mind we're trying to solve for x. So the first thing we want to do over here is distribute to get this x out of the parentheses. We can't solve it when it's inside there and trapped in the parentheses. So we have x log 5 plus 1 times log 5 is just log 5. Again, solving for x. So we need anything that has an x in it to be on the same side. So I'm going to subtract this term to move it over to the left. So we have 2x log 3 minus x log 5 equals log 5. Okay, solving for x. X right now is in 2 separate terms. So if we want to solve for it, we need to factor it out so it's out front there in one term. Not in one term, in one place. Now we have x times this quantity. So in order to solve for x, we divide both sides by that quantity. So that our solution is x is equal to log 5 over 2 log 3 minus log 5. We can do a little simplifying in here using our properties of logarithms. This 2 can be moved up into the exponent so that we have log 5 over log 3 squared minus log 5. 3 squared is 9. So, and these are matching logarithms. Log base 10, log base 10. Subtracted means we can combine those two. Oops. Almost forgot my log, log of 9 divided by 5. The 9 came from that 3 squared. We combine our subtraction here with division. So there's our final answer. This one only asked for an exact answer, so we don't need to plug it into our calculator. This is our exact answer. Number 18, Tamika deposited $5,000 at 9% compounded continuously. Find the time required for the amount to double using continuous compounding. So again, we have two compound interest formulas for continuous compounding. We want to make sure we're using this one with the E in it. Fill in what we know. Tamika started with $5,000, so that's going to go in for P. 9%, so that's our interest rate, 0.09. Find the time, so we're going to be solving for T. Find the time required for the amount to double. So that tells us the ending amount, even though it doesn't give us a value. If we started with 5,000, the time to double means we're going to end with 10,000, 5,000 times 2. So this is the equation we want to solve. We start off dividing both sides by 5,000. 10,000 divided by 5,000 is 2, doubling. That's where that comes from. To get that t out of the exponent, we can't solve for it when it's up there in the exponent. We are going to take the log of both sides. Specifically, I'm going to use the natural log because of this e. It's just going to make our calculations come out a little easier in the next step. Properties of logarithms allows me to take this exponent and bring it out front. So I have the natural log of 2 equals 0.07 times t times the natural log of e. The reason I picked natural log rather than log base 10 or any other base is because this is equal to 1. The natural log of e is the same as log base e of e, and that is equivalent to 1. So this basically, like multiplying by 1, goes away. Divide both sides by 0.07. And there is our answer. T is the natural log of 2 divided by 0.07. It does ask us to approximate to 2 decimal places, so we want to plug that into our calculator. Natural log of 2 divided by 0.07 is 9.902. If we round to 2 decimal places, that's 9.90. That's how long it's going to take her to double her money. I see my mistake now. Were you guys wondering all along this is not the answer on the answer key? I just glanced and saw that it's different. It's because I said 9% and then somehow I put 7% in there. Okay, so same work. It works the same way, but I have a copy error. I should have had 0.09 here, 9%. That would make this a 9, this a 9, this a 9, this a 9. Sorry about that. You were probably just going crazy watching me going, what is she doing? So natural log of 2 divided by 0.09, not 7. There we get the answer from the answer key. Sorry about that. Sorry about the confusion. 7.70 years. And number 19, a drug is eliminated from the body through urine. Suppose, oh, go away box. Sorry, I clicked on something. It'll go away in a second. Suppose that for an initial dose of 75 milligrams, the amount A of T in the body, yeah, go away. Come on now, computer. It's been working hard today. I want want you to disappear. Go away. There we go. Finally. Okay, number 19. A drug is eliminated from the body through urine. Suppose that for an initial dose of 75 milligrams, the amount A of T in the body T hours later is given by, we have a nifty little exponential equation here. What is the half-life of the drug? Approximate to 2 decimal places. So the question, what is a half-life? That is asking us for an amount of time. The half-life is the amount of time it takes for something to decrease by half. So if we started with 75 milligrams, 75 divided by 2 is 37.5. So the question here is, when will there be 37.5 milligrams of this drug remaining in a person's body? So that is our ending amount. So that goes in place of A of T. Our initial amount times our base raised to the power of T. Here's what we need to solve. We need to solve for T. So we've solved things similar to this before. We want to start off by isolating that exponential part of our graph, of our equation. So we divide both sides by 75. Then we want to take the log of both sides so we can pull that exponent down. Otherwise, we wouldn't be able to solve for it. So we take the logarithm of both sides. You can use log or ln. It doesn't matter. But that property of exponents pulls that t down front. So we then have the log of 0.5 equals t times the log of 0.8. Divide both sides by the log of 0.8. And then it just becomes a calculator problem from there. T is equal to log of 0.5 divided by log of 0.8. It asked us to approximate to 2 decimal places. So log 0.5 over log 0.8. Enter. So for 2 decimal places, we would look at the 6 and round up. So 3.11 hours is how long it would take for half of that drug to be eliminated from the body.